We want to switch gears now and go into our core areas of robotics. I know you've been waiting for this to see what we actually have under the hood. And as I mentioned to you earlier, we have those four areas defined in our website. And I'm going to now ask Jaemin Lee to kick it off and talk about human-centered robotics. And so Jaemin, Patricia will be holding a 2-minute warning.
Yeah, but I think, yeah, slide with the lead.
Thank you very much. My name is Jaemin from Mechanical and Aerospace Engineering. It is my pleasure to introduce our robotics research vision and long-term goal in human-centered robotics at NC State here. I'm going to introduce the work of a faculty member in College of Engineering. However, it is one portion of our broad faculty activities relevant to robotics. So I strongly encourage you to take a look at our webpage, called the College of Engineering Robotics webpage, and you can see a lot of an active research relevant to our robotics area. Okay? And for a decade, we have focused on building autonomy, that are building the machine very fast, powerful, and computationally very intelligent. But we got a lot of progress on perception, control, and even artificial intelligence, right? But we can think about the core question again. The previous question was how autonomous can we build a machine or robots? But we can rethink the human point of view. How can we design robotic systems that interact with the human, that live and work safely, intelligently, and more seamlessly? That is our core problem statement in human-centered robotics. Okay, so we are no longer think about very predefined and pre-allocated problem. So you can imagine everywhere we can put the robot where humans are. Robots are entering hospital, rehabilitation center, home, construction site, agricultural field, and even campus here. So we can think about what is real direction for our human-centered robotics, especially in NC State. That is our core question. So to guide that direction, we can frame our human-centered robotics in 4 dimensions, like human, with human, for human, and lastly, beyond human. I'm going to briefly describe each of these. First, like human. This dimension represents the work that robot can interact and operate naturally in human environment. You can imagine robot is walking around and the robot can do local manipulation. So that includes humanoid and animaloids capable of agile locomotion and dexterous manipulation. These two are very essential for human-like activities. So we can think about what is the main goal for this kind of humanoid or animaloid robotics. So our research thrust advances local manipulation, the integration of locomotion and manipulation. So we wanna put our humanoid robot and animaloid robot in the human-like task missions. That will be really challenging. Our research seeks to advance the fundamentals for agile and versatile local manipulation. So you can imagine what component we need for local manipulation. Hardware, algorithm, perception, software, AI, whatever we need. We can think about to deploy model-based optimal control, which is a little bit classical. Simultaneously, we can think about reinforcement learning and imitation learning to have very agile and versatile behavior, whole body behavior. Rather than separating walking and task execution, we can formulate our full body control problem here, like a human-wise. So we can make advancement like this kind of quadrupedal robot or humanoid robot, incorporating and combining model-based control and data-driven method, which is really data-driven. So that is the first thing. Second one is with human. So this dimension is about true collaboration. True collaboration requires understanding. So understanding, especially between human and robot. So here, one research provided by Professor Pengao in CSD department. So robot can recognize human intention and human preference. So they are sharing some vision, and then human deliver his perceptual and contextual information to robot, and robot consistently understand that contextual to do some collaborative missions, right? This is very important. So true collaboration is not just a command execution. We can think about collaboration is shared perception, shared intention, and adaptive coordination. We can understand how robot and human interact each other. That's going to be the most important question in human-robot interaction. In this sense, safety is really critical. So we can think about how to ensure safety while the robot is operating human coexistent environment, right? So safety approach typically use very hard constraint that severely impact in our performance. That is not a good way. Collaboration means we have to do a certain performance while guaranteeing safety. That is the goal. So we can think about how to reformulate our safety filter, minimally conservative. So the safest action is just to stand this here, nothing to do. That is the most safe action. But we don't want to do that. We have to dynamically adaptive safety filter let robot can do very active and efficient behavior while ensuring the safety. That's going to be one goal between robot and another robot or human behavior. The third one is for human. So this one is more relevant to wearable or assistive device. We want to make our robot can maximize some performance or functions of human. We want to make some robots for human being. So in that sense, we can think about some interaction between machine or robot and human here. Of course, we can program everything, but we have to think about how to connect the human intention, like a biosignal or muscle signal, to connect our assistive device. That is really challenging part. Another thing is like personalization. Everyone has totally different physical condition. We have to personalize it. Every robot has different physics simultaneously. Every person has different physiology. We have to understand how can we optimize or how can we make our robotic system going to be adaptable in terms of their physiology. And building like a computational muscular model going to be really important to understand human physiology and preference. So if we have a good model, then we can make a good controller for our assistive device. That is a really intuitive thought. We can think about how can we model our physiology or human model very precise That's going to be one challenging point. Lastly, beyond human. We can imagine our robot can make something beyond the human being. That's going to be really long-term goal. So we can imagine we are a robot symbiosis. So we are thinking about just a wearable or exoskeleton robot as just a tool before. But we can change the paradigm. We want to make some symbiosis device or symbiosis integration between human and assistive robot using reinforcement learning and classical control, even hardware as well. Also, another example is construction site. We can think about, we can put our robot in very hazardous or dangerous situation. Then human can guide high-level actions and decision-making. But robot can provide us our physical capability, right? That is a good combination between human action and robots enhancement. So NC State here, we are doing a lot of research study relevant to human-centered robotics. And then we have a more challenging problem, so we can make it better. We can make it more autonomous. We can make it more intelligent while really improving the human life quality. So that is what we are building right now. Thank you very much.
All right, and if you have questions or comments, there'll be an opportunity in the panel session that'll come after the break. Up next, we have Justin Bradley, who's going to talk about autonomy, perception. Let me just...
Should be good. It's close. All right, thanks. Hello, welcome. So I'm Justin Bradley. I am an associate professor in computer science, hoping to give you a brief overview of what we've got here at NC State in the realm of safe autonomy, perception, and control for robotics. So what I've done here is kind of scoured all the research happening on the sort of theory, on the autonomy side, and tried to synthesize that down into some key themes. I've also done a very deliberate job of plastering as many robot pictures as I can because nothing dispels the dryness of a talk about theory like cool robots. So please enjoy cool robots. So here's the roadmap that kind of came out after some synthesis. 5 distinct areas here. The last one's very specifically intended to be a cross-cutting area. Where each learning sort of exists in each of these sub-areas on its own, but then I've extracted it out in order to highlight, to kind of coincide with our AI initiatives. So the first area is safe autonomous control. This is answering seeks to answer the foundational question of how we guarantee robots behave safely in uncertain environments. The second is multi-agent coordination. This is where we think about scaling from one robot to potentially pairs of robots to potentially many robots, both homogeneous sets of robots and heterogeneous sets of robots. Third, the perception and sensing side, how robots see and interpret the world. Fourth, robot systems and verification. This is somewhat unglamorous if you think of terms of like nice theorems and proofs, more like, you know, if you want to take the theory and put it on a robot and make it work, how do you do that in a way that guarantees all the safe theorems that we've made? How do we then ensure that those translate into software and deployment? And then finally, as I mentioned, the learning enabled. This is deliberately cross-cutting and exists in each of the themes, but I've extracted it out. So let's get going here. So the first one here, safe autonomous control. So the idea here is how can we guarantee robots safely operate in uncertain dynamic environments? And this goes beyond just empirical measures, but provable, correct measures to guarantee assurance. So I think one thing that's exciting about the group that we have here at NC State is there's a lot of different ways that are being explored to do that. So we've got control barrier functions. These are sort of like invisible safety fences that constrain a controller in real time. We've got reachability analysis, where we're computing set of states of a system that it can reach and ensures that it stays within a safe set. We've got reduced order safety certificates that take a complex system like a humanoid robot and builds a principled smaller or simpler model, and then shows or proves safety guarantees transfer back into that simpler model. One thing that's kind of unique here is Lee brings some nice hot flasks algorithms. These compute exact solutions to high-dimensional optimal control problems, but without mathematical simplifications that usually make those solutions more approximate, which is quite an advantage for the nonlinear systems that really permeate the robotics world. On the cyber-physical side, I do work in co-regulation, which kind of seeks to jointly optimize both the cyber and physical side of that so that it's not just a physical certificate or a theoretical certificate, but also translates into the computational system. And Dr. Cohen's got some really interesting work on adaptive learning learning work that bridges into the learning theme. I'll talk a little bit more about that later. But the jumping around video here is his work. He's building systems that update their models online while maintaining formal stability and safety guarantees. And that's a really tough problem because no one is interested in your guarantees if they don't then translate under adaptation, right? Next big theme is multi-agent coordination and autonomy. The idea here is how we coordinate robot teams and collaborate in contested and uncertain environments. So there's some really interesting progression here of the work. Some of us have focused on how you coordinate and from a graph theory point of view. Some of us have used sort of the mathematical-based consensus algorithms. And then others have focused on how you do this with reachable spaces. One interesting work I want to highlight that's kind of been highlighted already is Dr. Gao. So he's got some really nice work on from the planning perspective, where he does concurrent UAV and UGV, that's air vehicle and ground vehicle planning, where they work together under operational constraints. The adaptive formation control work enables robot teams to reconfigure on the fly for collaborative gain or navigation. Another way to approach this problem is from the game theory standpoint. This is really nice. This work is done by Dr. Chakraborty. He models competitive and cooperative strategies for tasks like target tracking. And this is where agents may have aligned or potentially misaligned objectives and need to coordinate and strategize. So it kind of takes some of that autonomy and takes it to the next level. Once I have autonomy in place for a multi-agent system, how can I then strategize? And then I've done some work sort of trying to take some of that theory and then apply it to the field, deploy swarm robot test beds, as well as doing heterogeneous real-world deployments. So the next theme I want to talk about, perception and sensing. Here we're addressing the question of how do robots reliably perceive the world, and how do we ensure that those perceptions are trustworthy and accountable. So again, doing some great work here in our group for shared situational awareness via deep graph learning, as well as cross-modal sensing for heterogeneous robot teams. If you imagine sort of each different kind of robot is collecting different sets of sensor data, how do we sort of fuse that into useful information that we can share across the set of systems that we've got? Dr. Lobaton does some really cool biobotic environmental sensing. He's got as you can see, sort of the little computer attached to the back of a cockroach, which is super cool. These are what you might think of as cyborg insect swarms for mapping collapsed building. There's a lot of cool problems there, but I think some of the most interesting ones are if you have poor information, localization signals that you're trying to capture, how do you capture those in a reliable way? Some really cool work being done by Dr. Yoon is preserving the evidence of sensor compression and the chain of reasoning along of the full autonomy stack, so that you can indicate where that accountability should lie if something goes wrong. This is critical. If there's an accident, if something does go wrong, we need to be able to trace that stream of data. This is sort of where rubber hits the road, as it were. If you're going to deploy robots, you need a way to ensure that all the careful theory maps into the software and the physical computational system. So Dr. Ord does a lot of great work on ROS. His physical unit type inference tries to evaluate when there's a mismatch in the software regarding units and take appropriate action. He also works on some lightweight formal methods that are easily computable. Dr. Guo does some great work on the real-time scheduling safety critical systems side, making sure that in a mixed criticality real-time system, that is a system that's got safety critical tasks and potentially less safety critical tasks, how those get scheduled in a guaranteed way. And then wanted to highlight as well Dr. Mazzolini's work. You already saw his work. It was the crab moving through the sand. Really great mechanical design. And then the learning-enabled robotics, I mentioned a cross-cutting theme here. Basically, you could see throughout that, the presentation, different pieces of that learning coming through. Let me kind of close with a summary slide here. So I looked at 11 faculty across 3 different departments and kind of tried to show you how we take different sets of theoretical strategies and combine them into building trustworthy autonomy. We can do that in individual robots as well as multi-agent teams and swarms. And then that theory gets taken very carefully through development in software onto platforms and through deployment in our group. And that's all.
Great. All right, thank you. Okay, everyone. Very excited to be here. I'm representing, I'm representing technical difficulties. All right. Let me just ask the students in here to tell me if they've taken a course called MSc 200 or MSc 201. So we don't have materials, and we don't have materials experts, right? So I'm going to try to make the case to you that there are developments. We have a few, right? But there are developments in materials that enable future of robotics, but there are also very interesting opportunities for robotics to transform how material-based technologies are being developed. So we've been able to identify through our surveys 3 communities, essentially looking at using robotics for flexible manufacturing, advanced manufacturing. Another group that is using robotics in combination with artificial intelligence to do material discovery. That's going to be an interesting topic. Maybe you'll see how this might transform the way your lab works, right? Self-driving labs was mentioned. Good. All right. Thank you. Good. And and one more group that focuses on soft robotics. So that's going to be very kind of far out, but hopefully this is going to cross-pollinate some interesting ideas. So again, I was impressed by how significant these groups are.
how interdisciplinary they are, but also how cohesive they are. So for example, in robotics for manufacturing, it's really primarily coming from ISC, CAML, which of course is a very, very high-profile center for advanced manufacturing and logistics. You have activities in robotics for materials discovery, in chemical engineering, in material science and engineering. The materials for robotics effort is probably the largest one. And here it says 5+, but I think there are probably at least 7 people who are going to be represented. And I'm missing a couple of people here, but I was happy to see Lillian Shao is going to be presenting in the speed presentations. Sorry. Yeah. So you can see some examples here of robots working in a lab environment, and also some very unusual objects kind of jumping around, right? Very, very kind of far out there in terms of the applications. So let's start with robotics for manufacturing. I think here there's an interesting kind of cross-section of activities. Autonomous manufacturing is one angle where you have artificial intelligence that comes into play, and vision, and so on. I'll talk about that. I'll probably highlight that example with Dr. Fred Livingston. We also have, of course, a lot of activities in advanced 3D manufacturing. So you can think about a 3D printer, whether it's printing metals, polymers, ceramics, whether it is using additive or subtractive methods. You could think of them are kind of cyber-physical systems, robots, and there could be intelligence given to them. They could be combined to work together. So I think we need to really look at that as part of the whole robotics ecosystem. In here, there's also the opportunity to go down to the nanoscale. This is very significant. The ability to do 3D nano manufacturing starts to kind of bring you closer to microelectronics, using these adaptive, these manufacturing methods to do so. When you have multiple robots working together or working with people, thinking about logistics, for example, if there has economic and other benefits associated to it. So, and one very obvious example of a robot would be a self-driving car, right? And how would that coexist with our transportation system and human-driven vehicles is topics that are also covered. Human-robot safety, and a very important theme, I think that's going to emerge today, is also covered. So one example I wanted to kind of highlight is kind of looking at a problem, I think quite fundamental, and perhaps also people are going to see the connection with what's happening with drone warfare in Ukraine and so on, is how do we enable low-volume, high-mix manufacturing? And the connection here with Ukraine perhaps might be if we field a prototype, learn from it within a week or two, and come back and create the next prototype, right? That could be an example. Or it could be a customer that wants a product, another customer wants a slightly different version of the product. How do we actually manufacture these things at scale, but with this ability to create variations? So the vision here is to essentially enable this hybrid type of manufacturing, where you're combining 3D additive manufacturing, subtractive manufacturing, combination and assembly of complex parts in a collaborative way between robots, and to be able to do inspection, which is really important, right? And so the idea of doing digitalization using 3D vision that takes an object's geometry, turns it into a CAD drawing, and compares it to what was meant to be fabricated, right? So that's really, really sophisticated capability, and then using kind of digital twins and so on to be able to forecast or plan the next steps to be taken as multiple robots work together. The next area is, imagine now that the materials you're working with do not exist. Or perhaps if they exist, they're not quite at the level they need to be. However, we have a use case in mind. We have a technology in mind. And so historically, this concept, this has required our traditional research and development enterprise to take about 10 to 15 years to bring a product to market, right? And so this roadmap that you see, or kind of projection of acceleration, is actually happening right now you could see here kind of 10x, 100x, 1,000x acceleration of research through autonomous experimentation, right? And so we have some really leading groups here at NC State, starting with chemical engineering's Milad Abul-Hassani, with his autonomous fluidic nanomaterial synthesis, a new colleague who started a couple of years ago at NC State and is already making an impact, is working on electronic polymer synthesis. Ourselves, we work on translating these materials into devices. And we also have colleagues who are thinking about how do we incorporate AI associated to materials into these platforms. So let me start with kind of this idea that if you want to bring a technology to market, typically what we've done is we've conceived the material, we've gone into a lab and done synthesis. Another group might be taking these materials and making devices. And then eventually, if everything is working out, we might go to manufacturing. But this, essentially, there's a lot of failure in this process. And often this failure happens after a couple of years of effort, right? So all this kind of accumulates into creating this 10 to 15-year time that it took, for example, for lithium-ion batteries, for OLEDs to come to market, just as, as examples. So the idea here is, how do we close the loop between all of those? How do we integrate all these steps together so we could do co-design, co-optimization? And perhaps even as we're designing the materials, we're designing them at scale, manufacturing scales. And so Martin is kind of a leading, a thought leader here at NC State in this area. And I'm very excited to have a DEMREF project with him, an NSF DEMREF project that is looking at how do we design materials for soft materials for brain electronics using these approaches. Milad Abul-Hassani is also thinking about these topics and thinking about how do we go from atoms all the way to an end device, right? So for example, next generation display, infrared sensors, and so on and so forth. These are materials that have to be synthesized into quantum dots, nanomaterials, integrated into thin film devices, and then scaled. So together, we've built the infrastructure to be able to go kind of end-to-end in this area. And he has already had some tremendous success at the upstream level where we're synthesizing materials. And we're kind of building up the midstream and downstream infrastructure so that we could do this inverse design from device to materials. And I would say here that one of the key things is the perception that we need here is not just vision. We need perception of material structure and perception of material chemistry and material properties, right? So that's why I was asking about MSc 201 and 200. That's where we teach students about looking at the structure of materials, the properties of materials, the functionalities of materials. And essentially, our robots need to be able to do those things, right? They need to be able to be scientists. Like imagine a Mars rover basically in your lab with all the tools and everything and doing that work. And of course, on the soft material side, soft robotics side, there's really, really a lot of creative work that's happening. I really loved putting these slides together. And so there's work in sensors and actuators. Think about materials that go beyond what today's robotics can do to create really safe robots. Physically intelligent soft machines, and even neuromorphic bioelectronics to kind of build bio-inspired brains. And here's an example of self-healing. Think about how could this middle one here be self-healing when you actually cut the electrical wires. How is the LED still turning on, right? You have soft sensing, you have self-powering capabilities, and then you also have organic artificial neurons that behave very, very similar to biological ones and hopefully could inspire very low power computing and analytics. And of course, you're going to hear also from some colleagues, Orlin Velov in particular, how do we actually actuate? How do we move at different scales? How do we control these with electric fields and magnetic fields? How do we make them physically intelligent so that they can react to external stimuli by reshaping materials without having computational needs? And so I'll stop right there, and thank you for your attention. And I think that there's an opportunity for this community to be engaged by the robotics community and vice versa. and look forward to more discussions a little bit later. Thank you.
Thank you. So, hi, how's everybody doing? Almost to a break, okay. All right, so we think about, I get the great job of talking about how a number of investigators here at NC State are taking all these concepts that have been addressed and addressing them towards very specific applications. And I just wanted to pick out 3 applications: medicine, food production, and this idea of autonomous actors. So autonomous vehicles, but that not just cars, but especially drones. And we want to focus on these because we've got a number of investigators working in these areas. I think these are strength areas, and then also these are really important for the North Carolina economy as well, all these areas. Okay. So when we think about medicine, a lot of people think about surgical robots like the Da Vinci here. You can also have nursing assistants or physical therapy assistants, companion robots. Today, though, I really want to focus on rehabilitation. And that's this really intimate interaction between the individual and the robotic device, either in a prosthesis, where you're actually kind of filling in for replacing the limb, or an exoskeleton where you're working with the existing limb. This is an example of some work being done by Dr. Wong's lab. And here on the right, if we can get this going, is an example of a knee prosthesis that she's created. And here's the individual walking on the treadmill, and you can see them measuring the gait. And again, the idea here is being able to improve gait for somebody that has lost a limb. In the middle, you see somebody on the balance test, and this is a prosthetic ankle that her group developed, and it's using pneumatics to control this. And you can see that balance is a huge issue. And then over on the left, right, is this important idea of how do we allow the user to actually control these devices, and in this case, using EMG and using the signals from the residual muscles to be able to actually drive the system. Okay. This is from Dr. Sharma's group. So now let's say somebody has an intact limb, but they can't really control it due to some kind of neurological injury, such as a spinal cord injury. And here's where we can use an exoskeleton, which will actually go around the existing limb, but be able to drive, say, the hip and the knee in order to allow this person to stand, first of all, and then even to walk. Right? And you can think of this, the priority has got to be on safety, and especially avoiding obstacles. And so they've come up with a number of techniques to incorporate kind of safe movement of this device into the exoskeleton. And then they've also been combining this with electrical stimulation of the muscles. So we've got the exoskeleton plus electrical stimulation of the muscle. And we can give this combined system. It has a lot of physiological benefits, as well as possibly reducing the size of the exoskeleton we need. And in here, you can see the person kind of using this combined device, an exoskeleton they created. And then they can use ultrasound to look at the actual activation of the muscle itself as well, and see if the muscle's fatiguing. In my lab, we really focus on upper extremity, and on the left, and we should have demos of this if you want to see them in action, cable-driven exoskeleton. We're able to control from an iPad, so we can choose what kind of grasp we want. And then we can choose where we want to be in that grasp, how much you want to open or close. Right. We can think of these devices, though, not only being assistive, but could also be therapeutic. Right? So how can we help the person relearn or retrain their muscle activation patterns? And over here, we've got this pneumatic glove, which is just basically these air chambers that will fill and kind of force the fingers into extension or prevent them from unwanted flexion. And that can be used, basically somebody can practice with a virtual piano playing that. They can hopefully retrain their muscle activation patterns. Food production is also a big area. We often don't think about robots in farming, but this is a very labor-intensive field, right? And a lot of potential for these robots in a variety of activities for food production or even food delivery. Have many of you been down to the Charlotte campus? You've seen these food delivery robots running all over campus, sometimes running into each other. There's some great pictures you can check online. Right. First, I want to provide the work of Dr. Hall. He's the director of the Marine Aquaculture Research Center for NC State. And this is just showing some of the devices they've come up with. So over on the left is a sawbot. So it's actually delivering food out to these fish ponds. And you can see kind of the dispensary wheel here. So it's actually swimming out there to them. Then we've got this pontoon boat, solar powered. With numerous sensors you can see on this, right? And this device is going in measuring water quality and other features. And then we've got a drone here that can drop down and look at temperature and temperature variations among these fish farms. And I'd just like to point out in this graph up above that kind of the green line is protein produced by fish farming, and you can see how this is kind of really taking off. Right? Dr. Bai's lab is also looking at agriculture, but looking at crops and livestock production and how they can maximize productivity. So if we think about, even with conservative estimates, population is supposed to hit 10 billion within this century. That's a lot of mouths to feed. Right? And so we got to look at ways that we can hopefully maximize productivity. And they've got this device called an NU SuperCam that goes and will check out the fields. It reminds me very much of like an NFL broadcast, the way this camera works. But they're also working with some tractor-based platforms such that they can allow for automatic transplanting, such as for sweet potatoes or tobacco. Right. And this is Dr. Louboutin, his work. And what he's doing is looking at, you can think about these robots, right, based with cameras. And so they're kind of looking in, they're trying to find weeds or other stressors that might reduce yield. Right? And he's using this idea of digital twin, which again is this dynamic model that's continuously updated. And in this case, he's trying to see how many robots they actually need and how many views they need in order to fully capture the scene. When we think about autonomous vehicles, a lot of times we think about cars, self-driving cars, right? But I want you to also look to the skies, especially for drones and some ground vehicles and robotic swarms, right? So this is the work of the Aerial Experimental and Research Platform for Advanced Wireless, AirPaw. So I had to look at that. It was a little bit of a long acronym. But they've got sites both on Centennial Campus and over on the Lake Wheeler site, right? And they provide test beds to allow you to work with drones, ground vehicles, and others for research and rescue missions and some other applications. Here's another example of a digital twin. So you could basically kind of lay out your testing of your drone and see how it works in the simulation before you actually go ahead and build the device. And Dr. Sichtu is working a lot with actually building drones. So see, these are some of the drones he's fabricated, and you can see them in action. Okay. Again, this is over at the AirPaw test site and can be used in a number of hostile environments, such as for search and rescue, natural disasters, battlefields, that kind of thing as well. So now we can put a number of these drones together, such as Dr. Chakraborty has been doing, all right, to create swarms, possibly for defense. And you can think about now you've got to control not only an individual drone, but now it's got to respond to all of the other drones as well, right? And so you've got the swarm that's got to act as creating a kind of act in concert to achieve a single goal. And he's doing a lot of the concepts we talked about, combining model-based with AI and machine-based learning in order to train these swarms. Right. And Dr. Bradley presented earlier. I wanted to highlight some of his work as well. He's doing a lot of work with drones, and especially these drones interacting with the real world. So, soil sampling, leaf sampling, igniting fires, water testing, right? And again, working with these swarms that can create this. So just like to highlight a few of the organizations that are really underwriting a lot of this activity and directing a lot of this activity here on campus, and then also some of the sponsors that are supporting this work. So thank you.
Thank you, Derek. All right, so we have now arrived at our first break, but I hope that you now can see the depth of robotics expertise that we have at NC State, and they span multiple directions as well. You have theory, you have human-centered robotics, you have applications and novel materials. And so I'm sure you have comments or questions for speakers, but what we will do instead is wait for the panel, which will be moderated by Ellen Huang. And that will start at 10:30. And yeah, and also all the lightning talk speakers, please meet Patricia at the break for your order. That's going to start a little bit later. I wanted to bring the attention to the agenda on your tables, because we really have a very exciting lunch session as well. So after the panel, we're going to have a lightning talk session where we have multiple faculty members giving 2-minute overviews of their research. And then we'll go into lunch and poster presentations where we also have demos set up. So please make sure you check those out. And then at 1 o'clock, we'll have the robotics clubs giving their pitch. And you'll be very excited to see the level of robotics involvement of students at NC State. And then we'll go and move into education. And so at 1:30, we'll have a session moderated by, or run by Sterling McClure in computer science, and he'll talk about education. And then at 2:15, which is the last session of the day, we're going to have a brainstorming session on where we go next. And we have a couple of ideas to pitch to you, and hopefully we will be able to get your thoughts. So get some coffee, get some sugar, there's sugar there, and meet us back at 10:30. Sorry, it's a short break.
All right. Okay, well, it is a pleasure to have the opportunity to start the lightning session. And maybe this is appropriate because what I'll be discussing is one of the boundaries of robotics. So one can have robotics in space, which is the bigger boundary, but there is a small boundary, and this is the microspace. So one of the topics of research in my group has been how one can actually actuate, make small devices that are intelligent and that operate on the micro scale. And there are a couple of principles that need to be included here that need to be resolved. Basically, moving anything on the micro scale is hard, especially if it's a liquid, because of the reciprocity of the motion and the high viscosity from that scale. So this is really hard to make a small object move on the micro scale. Nature has solved this problem, we have to solve it. What you're seeing here on the left-hand side is how one can use AC fields in order to provide power for microscopic circuits that move on their own, that can interact and sense. And then there is the principles for magnetic actuation of micro-robotic type of devices. These are 3D printed microbots, a small microbot that captures live cell and moves around, and then a self-assembled magnetic microbot. So this is one of the potential directions. Those type of devices can be incorporated in ensembles and swarms. So I'll be very glad to discuss further as my poster. Thank you very much.
All right.
slide, Grudge. I will talk about AirPower a bit more, and we have a poster. If you're interested to learn more, you can come to the poster. I'm the PI for AirPower. So AirPower is a testbed, as Aranya and others discussed, in Lake Feeder. We also have some towers, actually, Centennial Campus. We cannot fly drones here, but it can be a great resource for you to interact with your robotics platforms. The nice thing with AirPower is we have a digital twin. You can program your software in a virtualized environment and then you move your software to the testbed. So my own research is at the intersection of communications, localization, and autonomy with AirPower. Just a few quick examples. We, for example, work with autonomous data mules that decide how to fly based on the communication constraints. We have work where you have 5G flying towers that can position themselves, also adapt their parameters while serving users on the ground, for example, after an earthquake or in the battlefield. We have work in localizing signal sources where the drones, they fly adaptively based on signal observations and they localize the signal source quickly. And we also can use the fixed infrastructure to localize things like drones using not only passive sensing, but also ISAC type of waveforms, where ISAC stands for integrated sensing and communication. We can use communication waveforms to as radar to sense. And I'll stop here. Again, I can talk more next to my poster. All right. I'm Minas Mikio. In case you wonder who comes with 8 slides, that would be me. But I'll be fast. Because funny enough, I don't do nearly as much in robotics than most of you. One of the things that I do is I'm responsible with building the drones for airport, and this is what we came up with. We designed it in CAD and manufactured it part by part, circuit by circuit, each arm, and we did that not once for our large drones, but also for our small drones. So that's one thing. I like to build things, and I build things. And the second thing is I enable programming of these things by working on a digital twin, right? So we have a digital twin that allows users to develop software in a cloud environment, and once they're happy, they push it to the test bed, they run it on the test bed, and the results go back to the digital twin, right? So it's a digital replica of our test bed. We have 3 fake things in our digital twin. We have fake drones, fake radios, and fake air for propagation. Everything else transfers from one to the other. And the results are relatively realistic, not identical, right? So you see results from flying in the field and measuring signal strength, and flying virtual drones in our virtual digital twin and measuring signal strength. Done.
Hey, good morning, everyone. I'm Brent Bai, Assistant Professor from Biological and Agricultural Engineering. So before joining NC State, July 2024, I have been working in University of Nebraska-Lincoln for many years. So at there, I co-developed parallel robots or cable-driven robots for plant remote sensing. You can see this kind of robots used in stadium for football games. So that's my background. And after joining NC State, basically we are doing ag robotics or ag automation to try to reduce the labor cost, so which is quite important for our growers, for farmers. So here, if you look at on the left, basically we are trying to integrate autonomous drones and also autonomous vehicle for precise crop management. So one example we are doing is for tobacco industry, which is quite important for North Carolina. So we will fly the drone and build the data pipeline, add a prescription map, which is the action map for the robots. And robots will go out to do topping and precision suction control for tobacco industry. So that is very good application, as my opinion. If you look at the right side, it's quite similar. It's always involved sensing, decision making, and action. So this is about precision livestock management. So one of the ongoing projects is we are developing a trolley system, which is autonomously moving in the oil warehouse, which is a very important industry in North Carolina. So without walking into the barn, which is a very dusty and harsh environment for the workers, now we can map the entire thing every hour. Then we send out a small-scale robots to autonomously go there, do intervention, and also remove the dead birds. So those are two examples of ongoing project I want to introduce to you. Thank you very much.
So I just wanted to make a quick note here that many of these people also have posters, so for more in-depth conversations, but there will also be additional posters that are not presented in the lightning talks, so just so you know.
Okay, good morning everybody. My name is Wentao Tan. I'm an assistant professor in chemical engineering, and I do control theory. Well, quite unexpectedly, even chemical engineers do a nonlinear systems theory, right? So, which is really, justifying why we need such a symposium. So, my technical approach is, using the so-called operator theory for nonlinear systems. As you know, nonlinear systems could be complicated, with dimensionality, uncertainty, noise, unsafeness, a lot of challenges, including these issues in robotic systems. And with the operator theory, really, we can do all these problems, including modeling your system, analyzing your system's properties, estimating parameters, designing controllers, designing observers, etc. We can deal with all these problems just like in linear systems, but nonlinear systems are actually linear systems in infinite dimensions. So while the infinite dimensional theory is challenging, and indeed it takes a lot of theoretical efforts to establish, this is becoming more and more of a reality due to the development of data science and statistical learning theory. So we aim to combine the learning theory and the control theory for all these purposes. So with that said, the message is, if you are looking for the solution to your robotics problems, especially the control problems, in a both fundamental and practical way, if you want to beat the nonlinearity to death, you're welcome to talk to me. Thank you.
Hi everyone, my name is Aranya Chakraborty. I'm from Electrical and Computer Engineering Department. My background is in control systems and also in extreme dimensional multi-agent networks. So many of the work that my group does is on target tracking and surveillance related applications for extreme scale network dynamic systems. We work on model reduction and model approximation, and also developing controls based on hierarchical optimization. Lately, we have also started moving some of the model-based methods into learning-based methods. So hierarchical reinforcement learning is another thing that another research direction that my students are pursuing. And lately, one of the more recent interests is to move from deterministic control into completely stochastic control, and how stochastics will play a role in determining learning and control of extreme dimensional robotic swarms. Collaboration interests, so I'm more of a theory and algorithm person, so I lack hardware labs and hardware robotics, so I'm very interested in collaborating with people who work on hardware experiments, machine learning and LLMs, and also radar and beamforming applications. Very interested in writing proposals with them. I guess we have to talk about funding, so if you're developing proposals for Army, FOSR, or ONR, I'm very interested in collaborating from the controls and model approximation, model reduction, those kind of sides. I don't have any hardware, Lego robots like this, so I'm interested in working with people who can do experiments for me for the hierarchical RL and control algorithms that my group has developed. I'm always looking for applications and experiments, and this is my contact information. You have my email address over here, and also my website. So if you're interested, please talk to me. I will be very happy to collaborate with you. Thank you.
They only give you 2 minutes, and I'm going to spend or waste part of it by showing you Star Trek video clips. So there, Star Trek Beyond, the Starship Enterprise. Something's coming at them, they can't look at it. Why? Because it is a swarm, it's not a one thing. It's 2350, and the Starship Enterprise is seeing a swarm for the first time. One wonders why. They shoot at them. Of course, the swarm things get out of the way, a few of them die. Nobody cares because they can go hit the thing in little pieces and take it to... This is painful. If you've been watching Star Trek for like 50 years, like I have, this is actually painful to watch. Try to run away, and no, that's not going to work.
So how are they communicating between each other? Do you think they're communicating back and forth from the cloud on Starbase 78, which is like 15 light years away or something like that? We don't know. But give it 1,000 years. Starfleet catches up. Star Trek Discovery, and now that's Cleveland Booker's ship. Is there not a single other Star Trek nerd in this room? Yeah. Okay, all right, fine. Few of us short. That's not what we do. I'm not saying that's what my students do. What we do are things more like that. So really, Vijay gave away my lightning talk. Thank you, Vijay. This is a good thing to say. It's going to be a lot of multi-bodied, swarm-based, swarm, platoon. Swarm implies some sort of mobility, maybe not necessarily that. And that's going to bring up a host of problems for networking, communications. This is Petri NetWest model for communication protocol one of my students developed, which basically guarantees that you are able to keep track of all your different bodies, different parts of your bodies, which are separated by ether, not wire. And that's, and if you lose some of them, you lose some of them. Maybe you gain some of them back, stuff like that. There's also other bunches of research on how parts of a different platoon can separately went through a network-aware, connectivity-aware sort of thing. Here's an interesting stuff that we just started. As soon as you do that, you can potentially get into spoofing and get attacked. And trust, physical trust generation in a bootstrap situation, nothing, no cloud in reach are important things. That's a particular thing where we have a set of a platoon of UAVs that actually wrap around the Fibonacci spiral and can encompass a roughly spherical area. This is something that we actually managed to fly just the other week, less than a month ago, in AirPod. You've already heard about AirPod. AirPod is also over there. Please take a look. Hi folks, that's me, Robotics. There's the day of the multi-bodied robots is coming, and communications, wireless and otherwise, some form of coordination. Thank you.
Thank you guys. I just remind everybody to try to keep it within 2 minutes. Thank you.
My name is Jishangu. I'm an associate professor in computer science. And what I do for robotics are guaranteeing timing correctness from sensing to actuation. Because robots, a lot of robots, or perhaps most of the robots that we care about, interact with the physical world in a timely manner. But today's computers or computing devices and communication devices, it tends to be designed to provide better average case performances rather than worst case guarantees. So if your robots face needs in guaranteeing worst case timing delays or responses, then I'm the wrong person. One of the platforms that we use is this 1/10 scale autonomous driving vehicle, and my student Kurt is holding that. I will demo that during lunchtime, and to see that how we design algorithms and use stereo theory and formal methods to prove the end-to-end timing guarantees for the systems like those. All right, thank you very much.
Hi, I'm Varun Nadam. I work at the Neuromuscular Rehabilitation Engineering Laboratory, led by Dr. Helen Moon. Our entire lab is driven by the need to develop robots that can improve quality of life, independence, and agency of people with physical disabilities. So what we do is we develop robotic processes and exoskeletons. These devices, in addition to being an interesting robotic problem, are also a very interesting physical human-robot interaction problem. The reason for that is that these robots are actually directly connected to the human to restore machine joint function, or connected in parallel to existing joints to enhance their function. Which means that any small misinteraction between the robot and the human would cause injuries, falls, and other adverse effects. So we aim to address this problem by a concept we introduced called wearer-robot symbiosis. Now this concept is where we explore how two intelligent systems, the human and the robot, can interact together to ensure that they can coordinate with each other and they can adapt to each other's needs. And we do this through a three-step process. The first step, we design the robot, which means that we develop our mechatronic systems to have all the sensing and embedded systems to ensure that this interaction can happen. The second step is the interface, where we develop use neural signals and AI-based control, mostly reinforcement learning, to ensure that the control can actually personalize and adapt to the user's needs. And finally, the human. We actually look and understand how the human responds to these robots, specifically by looking at biomechanics, the cognitive load, the perception, or how they perceive their body image. And we use this to further develop our robots. Through this cyclic process, we have developed multiple robots that have enhanced mobility, balance, and manipulation for people with disabilities. And you can see our demos out there. Thank you.
Hi, good morning. I'm Jane from Canada Aerospace Engineering Department. So my research more focused on soft robotics. So our goal here is, like I said here, physical intelligent soft robotics. So we're trying to, reduce the control burden, by utilizing the intelligence from the structures, for example, structure designs and also materials intelligence. So it's called like the smart materials or intelligent materials, especially for soft materials. So I'm showing three cases. I think there's three examples, right? So one is the origami breakers. We call it universal flexible origami breakers. Can do a lot of things. And then the second one is underwater soft swimmer. So we are showing here through the mechanical design. Actually, we can only need two inputs. Actually, input to control 3D maneuverability, to do something like that. And then the last one I'm showing here is like magnetic soft robot. You can use remote magnets, right, to control carry the drug or carry the liquid inside, and then do the dispensing or delivering, through this kind of standard model there. I think, the application side is wide. It can be underwater, land, and space, and also for the agriculture things. So, if you're looking for someone, to work on structure design on the material side, so maybe, we can talk and then hope to for the collaboration here. Thank you.
All right. So 5 speakers left. That means lunch in 10 minutes. My math is correct.
Okay, so hi everybody. My name is Aritra Mitra. I'm an assistant professor in the EC department. So I use tools from control, machine learning, and optimization to design robust and data-efficient learning algorithms for large-scale systems. How is this related to robotics? Well, if you think about how robotic manipulators are controlled, we now use data-driven approaches, which are also known as reinforcement learning as. But surprisingly, even for the most popular RL algorithms, we don't really have a clear understanding of why and when they work, and how much data we need to provide precise accuracy guarantees. So this is where my group contributes towards the theory of reinforcement learning algorithms. On a related note, if we want to deploy these algorithms in harsh real-world adversarial environments, we need to think about how to contend with imperfect data that can be long-tailed, data that contains outliers, data that can be adversarially contaminated. So this is yet another prominent theme of my research. So everything that I talked about on the left is pertaining to a single robotic unit. But as we heard today, there are several applications in dynamic persistent monitoring, surveillance, target tracking, where you need a bunch of robots to kind of coordinate and come together. Okay, so in this space, we have a lot of work on multi-agent estimation, inference, network control, federated learning, where we think about privacy, security, information constraints, and how realistic communication constraints affect the accuracy of learning and decision-making algorithms. So if you're interested in any of these topics, please feel free to reach out to me.
Hello everyone, I'm Edgar Loarton from ECE. So our lab does a lot of work related to agricultural robotics. You might have seen some of that earlier. We also do some work on biomedical robotics as well too. But today I'm going to talk a little bit more about biological robotics, some of the things that we're doing in here. So we have some earlier efforts on biobots, as you can see in there, right? So our collaborators like Bosco and Mihail doing work on the hardware and the communication aspect of it. We focus a little more on the modeling of the behavior, how we can actually use that for control purposes, how do we use distributed sensing to destination, kind of like researchers of Islam and things like that. More recently, we have some other projects where we're looking at underwater freshwater mussels. and we're looking at their behavior, so we're modeling them as robotic systems as well too, trying to characterize the configuration space and trying to take advantage of some of the uniqueness of the sensing and the behaviors to try to basically track things like the amount of pollutants on waters and things of that sort. So we're working on that direction as well too. So the other line of work related to this is also some of the microscopy work that we're doing, where we're incorporating a lot of digital twinning of microscopic fossils, for example, or also living organisms such as nematodes, to try to kind of characterize the behavior again, their morphology, and then take advantage of that and the digital twins to try to build more efficient type of like 3D imaging type of systems related to that. So there's a lot of optimization involved in that. So if I'm going to mention maybe 3 things, I guess, that my lab does, is that we integrate geometry, we integrate probability, and of course we integrate physics as well. I'll stop there. Thank you.
So imagine you have all these people that have all these cool robotics research, and you're wearing a device on your body that can do all these things, sense the environment, maybe do your homework for you, maybe write proposals for the faculty. It's very awesome. It's a very awesome piece of device. But you wear it, and the first thing you feel is, ouch, it's uncomfortable. So our lab actually thinks about this particular psychological aspect from the material standpoint. I'm Lillian Xiao. I'm in chemical and biomolecular engineering here at NC State. So we think about soft materials because the human body is soft. A lot of biological systems are soft. We need to think about softness as a very important robotic and mechanical aspect of materials. In our group, we think about haptics, and that's tactile sensing, movement, and also things like friction. Friction can generate electricity. If you rub your skin enough against your tablecloth or something like that, it will generate static electricity. We think about fundamental aspects of this interface that generates different types of friction, power, energy harvesting, and you can see here on the right-hand side, we have actually very good knowledge of what happens inside the material at the microscopic scale. For example, we're collaborating with Amit van Dordkraft, who's in ECE, and you can see some of the examples of the collaborations here, where we look at things like energy harvesters, we look at things like making robots sense their environment and move in different ways. And for more details of the work that we're doing together with Amit, please stop by the poster. Our poster is going to be presented by 2 really awesome graduate students in ECE and CB. Thank you very much for your attention.
Hi everyone, I'm Martin Seifert, an assistant professor in material science and engineering. So when we design materials to try to discover materials, we face a really challenging problem, which is that we have these very, very large multi-dimensional spaces where the response surface is definitely not smooth. If you change some small thing about the structure of the material, its properties change drastically. And so for the longest time, it's taken forever to develop new materials or new processes. And I would also argue that we're probably missing the optimal point when we do kind of one factor at a time optimization. So what I'm working on is developing these self-driving labs to help us accelerate material development. Right? What are we doing there? Well, we're integrating AI or machine learning and robotics to actually do better experiments and do the experiments more efficiently. And that involves using machine learning algorithms. We do a lot of Bayesian optimization, for example, in the design and analysis parts of the design, make, test, and analyze cycle. And then we also use robotics to make new materials as well as test their properties. So, for example, we synthesize new materials using these automated pipetting robots, generate mixtures and formulations. Here we're generating a NC State logo. We also work a lot with thin film materials, so we fabricate and process thin films and we can characterize their properties. All of this without human involvement. The benefit there is you also have much better reproducibility. We like to think that as humans we're very accurate, but we're not. What humans are very good at is being adaptable. Right? The robots can do something over and over and over the same exact way. And then lastly, a lot of what we do is also developing flexible, low-cost, and open-source robotic platforms to make it a lot easier to integrate these kind of self-driving labs and research. Because a lot of these systems right now are quite expensive. And And so building open source systems is going to be very important. That being said, we're definitely not experts in robotics. And so if this is something that you think could be an area of collaboration, I 100% welcome that. Thank you.
Hey everyone, I'm Max. I work on using tools from control theory to design safe, autonomous systems. So let me tell you how I think about this. So this is a video of a robot walking around. It turns out we actually understand pretty well how to model the motion of the robot, right? So physical systems, physics tells us how they move. I work in a field called control, which I like to think of as how do we sort of design the forces that should be imparted on the system so that it moves in a desirable way. Right, so if my robot has actuators, let's say motors and certain joints, how do I control those things to coordinate movement? Okay? And really what this is doing is sort of changing the physics of the system such that your robot can do exciting things like backflip. This is not my robot, I cannot do that. So doing backflips is cool, it's pretty interesting, but really what I'm interested in is how do you design controllers for these systems so that they're safe when you put them out into the real world? So that's the main sort of research focus of my lab. There are a couple of different sort of sub-thrusts that we work on, lots of different sort of platforms that we work on, things like drones, using simple physical models to design complicated algorithms for systems. We also work on sort of hierarchical control in the sense of using a lot of sort of putting together simple components, again, to now try to make a system do something somewhat complicated. And then also working on using AI and learning to get systems to adapt in real time to novel problems.
And I'll play that again for another second, but that's kind of loud. So with that, thanks. I don't want to keep you guys from lunch.
Before we go deep, we have one more added slide.
I wanted to just show you a slide that was sent by John Muth, who could not be here to talk about it. But I'll just quickly flash it up there. And there was a comment that was made earlier about maritime robotics. So there's an effort here to grow that in maritime robotics. There's an initiative on the bottom right that indicates that North Carolina is well positioned for maritime robotics. And the expertise that NC State would bring to that would be optical communication underwater. So if you want to learn more, you can contact John.
Great. So I think we're all ready for lunch. And we're going to be meeting back here at 1 o'clock. Make sure that this academic speed dating thing that we just started here continues at the poster session. And I asked the student groups who are going to be doing, the clubs who are going to be doing demonstrations to be here 5 minutes before 1 o'clock. We're going to line up here. Thank you. All right, let's thank all the speakers again.
AI in robotics research.
Yeah, I can start. So I'm going to introduce some robotic centers and test bed. And we can discuss about how can we develop our own test bed to make a synergy here at NC State. And Aranya will introduce additional project and funding-wise, how can you build our test bed efficiently. So that's going to be our first agenda. So please feel free to discuss about this agenda. This is not a presentation session, right? Okay, 20 minutes. So I prepared 4 top schools. Stanford, CMU, and Michigan, and UT Austin. So they are leading, robotics program. Especially, they have their own initiative to bring the leadership in the nationwide. Especially robotic centers, and at Stanford, they have very interesting part. I can see like 9 pictures on their website, and they don't have any humanoid walking bed. So instead, they do like a underwater humanoid concept. They change the application. So it looks like application-wise test bed selection. So instead of choosing ground locomotion of humanoid robot, they choose underwater application to deploy humanoid robot. So that's going to be one interesting part in Stanford. And then they also create like a home-style test bed, as you can see in the second block. They put the bed and bookshelf, everything really similar to home style, and then they try to operate the robot in that test bed. That's going to be also one interesting part we can think about, because they have really specific target of their service robot. They want to put the robot in home environment like this one, bed, and then some bookshelf, everything going to be prefixed, and then they want to put the robot there and test all the algorithm and planning, controller, whatever they want to do. Okay? What they do is just put their own robot there and then try to demonstrate some daily life activities and so forth. And the third one is Da Vinci, medical robot. They put some medical robot devices there and then try to build a new controller to make a more precise and compliant controller there. And then the third one is space robot as well. As you can see here, the sixth picture. That is not totally identical to Mars, but they can imagine how can we execute some task in space or something like that. So that is not a big piece, but they are preparing space robot as well. And actually, the CMU side, they build a new robot, so they don't have enough information. But as you know, they also have a National Robotics Institute. They are pretty strong initiative. They have a bunch of test bed, like not only locomotion manipulation, rehabilitation, they have everything. So that's going to be really impressive part. And then University of Michigan Ann Arbor built a new robot center here, sponsored by the Ford, in my opinion. So they also have a pretty, many indoor-outdoor experimental test bed. Not only mobility, but also rehabilitation, and even like a 10,000-gallon research water tank. They are also focusing on underwater robotics as well. And then they have like a Mars yard imitation Martian rock. So they are also targeting the space robot. This is the intersection between Michigan and Stanford. And then UT Austin has similar building here to focusing on the robot. And then one thing here is they have a mock apartment, which is really similar to Stanford one as well. Likewise, they are blending like a application ergonomic test bed and application-wise test bed. They are blending both of them. That's going to be one trend for this universities test bed and robotics center. And
yeah, and also to add to that list, let me show a few other robotic test beds and initiatives that are also going on. So the first one in the list is the Robotarium project, which is actually not that new. I think this is almost 10 years old. And this was actually, the PI for this project was Magnus Egerstedt at Georgia Tech before he moved to UC Irvine. And this was funded by the MRI program, the Major Research Instrumentation program at NSF. And this was really a first of its kind type of a test bed because it allowed remote login from users all across the world. They can log into the system remotely and upload their codes in whatever software platforms they are using, and then those codes will be used for running experiments on ground robots that they have in this test bed, essentially. Ground and also aerial robots. So what they don't have is the underwater robots, essentially. So just want to mention this one because if remote login access test bed is one option for us, then we can pursue those ideas. And then I also wanted to show to this audience two other test beds which are actually they are not robotics test bed per se, but they are very related to robotics and can be applicable for robotics research. So the first one is actually a test bed. It's a part of the Mid-Scale Research Infrastructure 1 program
when I was at NSF, I was actually the engineering representative in the mid-scale RI1 group, and I was a part of the program directors who funded the Sphere testbed, which is a cybersecurity testbed which is run at the Information Sciences Institute at University of Southern California. So that's more like a distributed computing and cloud computing testbed where the focus previously was on cybersecurity, but now they have extended to like many other applications. So, so federation with these type of cloud computing testbed, I think, can be very useful for at least for the for the distributed control and navigation and SLAM type of tasks that are going on at the algorithmic level over here. And the second one, I guess, the faculty from my colleagues from the computer science department will probably be conversant with this already. The Fabric and the Exogeny testbeds that are already running at the Renaissance Computing Institute, RENCI, and Duke University and UNC Chapel Hill, which is also a distributed cloud computing, actively running distributed cloud computing testbed. I think the computer science is already federated physically there's a connection between NC State and that testbed. So these are unused resources that we can leverage for running a lot of experiments for our robotics faculty. And then before I turn it back to Jamin, I just wanted to mention, this mid-scale research infrastructure one initiative that I mentioned. I was a part of this program when I was working for NSF. And it's a foundation-wide program, so all directorates and all divisions can submit proposals. The mid-scale program has RI1 and RI2. RI1, the funding is, I think, from $400,000 to $20 million, and then RI2 is from $20 million to $100 million. These are the next steps for the MRI program, which ends at $400K. And there are two types of proposals. One is called design. The other one is called implementation. Design is more like if you are not ready for actually implementing your testbed, you can design like a prototype. So that's like preparing like a blueprint of your project. So that's design. And then I guess for us, we will probably be more interested in implementation because we already have several of these ideas, like Derek, for example, already has robots in his lab and stuff, right? So we are not in the design phase anymore. I think we are ready for implementation. And implementation projects, you can ask up till like $20 million for the RI1 program. If you want more, then you have to go for RI2. This is bi-yearly, so it happens once in every 2 years. And the deadline for pre-proposals, extremely competitive, by the way, so don't get your hopes too high because there probably will be like 2 or at most 3 awards in all of engineering. That includes quantum, that includes AI, that includes cybersecurity, cloud computing, everything, not just robotics, power systems. And the deadline for this year is September 1, 2026. So we have enough time if you want to write a pre-proposal for any of these robotics initiatives. So just wanted to give that as an FYI. So thanks.
Okay, thank you. So we would like to bring up like 3 questions here based on my searching activities. The first question is, should an NC State-wide robotics research testbed focus on specific platform, or should it be designed as a modular platform organic infrastructure to maximize long-term flexibility and collaboration? So this is going to be one part of discussion. So I don't have any answer because as you can see in 4 universities' case, they have their own atmosphere. They have their own combinations. So I think, I categorize 2 things here. For instance, one is ground mobility, aerial, global, marine, virtual environment, AI, whatever here. We can make a room for each of these. That is one option. Otherwise, we can think about specific application here, like agriculture, defense, healthcare. Then we can try to mimic that environment. We can operate our robotic system there. That's going to be another option. I think this is open question. So we wanna, listen to your opinion. That's going to be our, goal in this discussion section. So any suggestion or comments for that?
Now?
Yeah.
Good.
Thanks for prepping all of this. So for this question, I would kind of lean towards your second suggestion, modular platform agnostic.
Yeah.
And I say that because there's a lot of redundancy in the robotics labs that people have, right? Like, you have a lab with a motion capture
Yeah.
system. I have a lab with a motion capture system. There's probably 5 of the faculty that have a lab with a motion capture system. And so I feel like, it doesn't make a lot of sense for the university to be like, keep reinvesting in all of these things again and again and again for each faculty when we could sort of pool resources together to have these more modular platform independent spaces, and then allow faculty, like you're working on humanoids, someone else working on drones, to then bring in their platforms to that space that they can then use, right? And you can have it set up for, you can have it sectioned off to maybe emphasize different applications like you have up there, like, right? Maybe part of that space is, some sort of healthcare setting or agricultural setting. That's just my
Yeah. Yeah, thank you. That's going to be a really great idea. So I had a discussion about, that agenda with my another faculty in other university, and they said it depends on availability and research level, in my opinion. So for instance, locomotion-wise, I want to stabilize my locomotion in ground terrain without any obstacle. After that, we're going to bring the robot in a specific scenario. So depending on the, research phase, we can select, the environment, in my opinion. So that's going to be a really good idea, in my opinion. Yep.
Yeah, thank you. I would also lean towards the second option, and I think that, for example, specifically in this material discovery space, self-driving lab space, one of the big limitations we have is the availability of lab robotics, right? But what I mean by that is it's not just manipulation, it's also kind of the intersection of scientific instruments and robotics that allows you to do kind of domain-specific robotics. I think the modularity there would be extremely powerful. And at the same time, in our disciplines, we're not specialists in building robots, right? So I think, again, there could be a lot of cross-pollination and sharing of resources and sharing of skills.
I think Dr. Duncan. So there,
Yeah, thank you so far. I agree with all the previous comments. Sterling, thank you for your presentation earlier. In one of his slides, it showed that a lot of the new programs are centered in clusters around industry relationships. And here in North Carolina, we have a unique situation where we have agricultural, defense, and healthcare as our nearest neighbors. And so it will make sense for industry partnerships to have a test bed that has these modular platforms, but also has industry involvement for career development, recruitment, and maybe even sponsorship. So I think we should consider that when we think about our test bed platform.
Yeah. Actually, that's a really good question. We're going to connect that question to second one.
Yeah, is there, sorry. Yeah, I'm just wondering, in this, particularly at this juncture, perhaps one way of distinguishing oneself is to choose an environment where perhaps there aren't that many players. And in saying so, could we perhaps think of a test bed that could interpolate across some of the strengths that are endemic to North Carolina, NC State, or perhaps across UNC, or perhaps, so that you pick and choose, and then you interpolate. And now, in fact, we just hosted a candidate last week or the week before that talks about this generalization across from cost effectiveness and all that stuff, generalization of robotics across many action spaces. Can we do that instead of perhaps picking one of these? Do a few of them, interpolate, and then pick your strengths.
Yeah, I think if we have to go for like those bigger funding opportunities, then that's like a necessary condition, right? Because you have to be very distinct compared to Robotarium. You don't want to be, repeat Robotarium number 2, for example, because then the reviewers won't like it. So we have to.
But the innovation would be perhaps that.
Yeah.
Pick your strengths.
Right, and so the innovation has to be very, very distinct compared to what's already going on.
So in terms of the question, the diagram posed by the question, if I just go with that, it does remind me of the, if you want to go fast, go by yourself, and if you want to go far, go with the group. And in the morning you said multidisciplinarity is what, so obviously you have to start with focus and hope to broaden. Academia is supposed to have a broader horizon, more like a 25-year future or a 5-year future, but then this kind of thing is going to take a good amount of, for want of a better word, or politic word, I'm just going to say investment. And there, I wonder if the question is up to us. Maybe more what we can get, and maybe more short term is what we can at some point hope to get. I would certainly say let us keep the long term in mind, because otherwise we're going to leave a lot of people by the, on the side, and then they're not really going to be part of it. I feel like this is one of our opposites of strength, is that we can't always find a way to not compete internally, but rather collaborate very effectively internally to compete well outside. So yeah, I very much go for the second one, if we can manage it.
Okay. And second question is relevant to the question. So I think we need to make a closed loop to incorporate our end user or industry, whatever. How can you build this ecosystem? That's going to be really important when we think about the test bed as well, right? So as we mentioned in previous slide, we have agriculture, defense, and healthcare. How can we let them know our test bed and our research contributions? That's going to be one important goal of our test bed, in my opinion. So do you have any idea?
So one idea can be, and let me ask my CS faculty members again, especially the ones who are connected to AirPaw. So before you guys applied for the AirPaw project, did you do like a user conference to do like a survey of who the potential end users will be?
I'm just going to stop you there and say that AirPaw is multidisciplinary, and the lead PI is from ECE. Right. So, I'd love to answer for Ismail if he has.
Yeah, Ismail left actually, yeah.
Okay. We did a pretty extensive survey.
I see.
I think we sent it up to something like 50 plus universities, so we got, and other organizations, and we got we can supply that later.
Yeah.
I want to build on your question and maybe ask Scotty, is there an opportunity like this in agriculture where we can talk to industry and the appropriate stakeholders in agriculture who understand, show them what we have, but also understand what they're looking for 1 year, 5 years, 10 years down the road?
So across North Carolina, right, the agriculture is very, very large. And so working with commodity groups does provide a direct end user mission-driven type of approach. And that kind of networking does open up a lot of opportunities across both the College of Engineering, College of Ag and Life Sciences, and the university.
And then last question is about operational model. So this is really important because it is relevant to our availability and performance as well. So you can imagine how can we access the equipment and maintain all the facilities and robots and data sharing as well. That's going to be really important for keeping our collaboration in a test bed. So do you have any suggestion? Yep.
Thank you. So for less established areas of this interdisciplinary framework, there are areas that are at the bounds of robotics, but not core. I would say that one of the challenges is being able to build so I would kind of advocate for an operational model that on the back end of the test beds also has prototyping, and skills, technical skills for building any type of robotics, building, assembling, integrating, and that could be actually operated by our students. It seems like we have really, really competent students, and it could be really good experiences for them. And they could also be involved with all this interdisciplinary robotics efforts that are going on and support it. So that's kind of how I would, my suggestion.
Yep.
Okay, thank you.
Yep.
Thank you, Jamin and Aranya, for your discussion here. We're going to move on to the last part of our program today, which is going to be led by Edgar. And this is the last topic, but definitely not the least, and perhaps one of the most important driving forces in robotics.